Mindsetters, welcome to today's grade 11 maths show. Today we have a special revision lesson on trigonometry. We have selected highlights from lessons shown earlier in the term to help you revise. Please post your comments and questions on our Facebook page on facebook.com/learnextra or on Twitter @learnextra so we can help you with your revision. You can also download the notes for today's show from learn.mindset.co.za or click on the link on our Facebook page. Now it's time to get on with today's lesson.
Let's look at the graph y equals cos x. So what does this graph look like? And we're then going to sketch the graph. Let's sketch the graph y equals cos 2x. Okay, so we've been looking at the amplitude change, we've looked at the vertical change. Let's look at what happens if you double the angle. Grade 11s with your arms, can you show me what you think happens to the graph? Does it go up? Does it go across? Does it stretch across? Does it compress? What does it do? Okay, we're going to have a look at that in a moment. So let's firstly look at the parent graph. Okay, and we do that for every single one so we understand how the transformation is going to work. If we have 0 degrees, what happens? If we have 90 degrees, what happens? If we have 180 degrees, what happens to the parent graph? 270 and 360. Okay, cos of 0 degrees is always 1, that's where its maximum is. 90 degrees we have a 0, at 180 we have a minimum, 270 we have a 0, and at 360 we've got a maximum. So for the cos function we have two zeros, a period of 360, and we then have two maxima, which is very different from our sine curve. We have two maxima at 1, but we still have a minima at -1. So we've got those maxima at 0 and 360 degrees. So every 360 degrees we have a maximum, and every 90 plus 180 degrees we're going to have a 0, and then we've got a minimum at 180 degrees. Okay, now if we look at the graph y equals cos 2x, we're now going to find that at 0 degrees, we're going to have twice of 0 would still be 1. But at 90 degrees, we're going to have 90 times 2 is 180. So we're now going to have the 180 value. Now, this is very interesting. If we have a maxima and a minima, what are you expecting that curve to do? Where's it going to go through? It must have a 0. So it has to have a 0 here. Okay, it's going to have a 0 there. And then if I substitute in 180 degrees, I get 180 times 2 is 360. And the cos of 360 is actually 1. And between -1 and 1, there's also going to be a 0. And then it repeats itself. So notice very interestingly that the period of that cos function, because it goes from 1 to 1, for 180 degrees, it must mean that the curve starts repeating itself every 180 degrees. So we actually say that the period of the function is 180 degrees. And how do we get that 180 from the 360 parent and the coefficient of 2? Can you see that relationship? So the period of any cos function will be the period of the parent graph of the parent divided by the coefficient of the angle. So that's how we're going to find every graph's period. So we actually have the period of this yellow function is 180 degrees. Now there's something new for you because you've only ever worked in grade 10 with trig functions where the sine's period is 360, the cos function has got a period of 360, and the tan function has got a period of 180. All of a sudden, we've introduced a coefficient into we've given the angle a coefficient, and we have found that to get from a maximum to a maximum, it takes 180 degrees. And the way that we get that 180 degrees is if we take the period of the parent and we divide it by the coefficient of the angle. So when we're wanting to sketch this cos 2x, we're going to sketch a maximum at those points. We're going to sketch a minimum in the middle, and then what's going to happen in the middle? We're going to have this 0. So if I have to now plot the values, let's just do that. The xy values, we would have 0 degrees to give me a 1. And then I know that I'm getting a minimum -1, and I'm getting a maximum here at 180 degrees. So here I'm getting a 1. That means halfway I must be getting a minimum, and halfway between 0 and 90 I'm going to be getting that 0. So if we now test 45 degrees times 2 is 90 degrees, and the cos of 90 is 0. And halfway in between is 135. And that gives me a 0 as well. So you'll notice that from its first maximum, from its first y value, it will take us 1, 2, 3, 4 other quadrant angles to get 480. And you literally can go, you can go halfway, and then you can go halfway, and you can go halfway, because the quadrant angles are separated equal. Or you can say, I'm going to plot every, since I need 4 out of those, 180 degrees divided by 4. And with that, that means I'm plotting every 45 degrees. So you're always going to divide by 4, because you've got 4 quadrant angles, 90, 180, 270, and 360. So there's always 4 quadrant angles. So that's kind of standard. So my period is affected by the coefficient. And once I've got the period, I can then work out what the quadrant angles should be, or the new quadrant angles. So in other words, I'm going to get 2 cycles between 0 and 360 degrees, because as you can see, from 180 to 360, I'm going to have another 180 degrees, so my cos function is going to repeat itself there. Okay, so this 2 is also a nice value that shows how many cycles you have in the parent's period. So in 360 degrees, we're going to have 2 cycles. Okay, so let's just finish that off with y. What about y equals cos 3x? Okay. We will always start with the period. What is the period? How often does that cycle repeat itself? It will be the period of the parent, which is 360, and we're dividing it by the coefficient of the angle. So my period is 120 degrees. Okay. Now we know we need to find where is it going to be maximum, where's it be a 0, where's it going to be a minimum, a 0, and a maximum. So where are those quadrants going to be? How many of them are there? 4. So we're going to plot every 120 degrees divided by 4. We're going to plot every 30 degrees. So I now know that if I have 0, I'm going to have a 30, I'm going to have a 60, I'm going to have a 90, and I'm going to have a 120. That's my first cycle. So I'm going to have a max, then I'm going to go to 0, then I'm going to go to my minimum, then a 0, then a maximum, and that cycle is going to repeat itself. Now, grade 11s, you're often given a domain. Don't look at the domain. Work out your cycle first before using that domain. Work out its repetitions, and then from the domain, go and trim your graph. Don't let the domain distract you, because your first primary focus point within trig is to look for how this cycle is repeating itself, and how it's repeating itself, and what its period is. What is its period? What is the y values? And then plot it. Notice I have not used a calculator. I'm trying to understand how the function transforms based on how the parent graph is changing as a result of that changed coefficient of x. Okay, so that's that function. And so if we use the parent graph features to sketch, let's sketch y equals tan 2x. Okay, it's a coefficient of the angle, so what changes? Great, the period. So the transformation is that there's going to be a period change. And what is the period going to be? Well, the first thing to ask ourselves is, what is the period of the parent graph? So y equals tan x. What is its period? Its period is 180 degrees. So I take 180 degrees and I divide that by 2 because the coefficient is 2. So what I'm saying now is that that curve, that tan function, will take 90 degrees for it to repeat itself. Now, how does the tan function behave? Okay, in the parent graph. Let's have a look at that. So if I have y equals tan x, how does it behave? I would have a 0 at 0 degrees, and I would have a 0 at 180 degrees. Halfway, I have a line that breaks the two curves. So at 90 degrees, I have an asymptote. And then at 45 degrees and at 135, I have these special values of 1. So the function approaches the asymptote, and over here, it approaches the asymptote at -1. So my graph is actually made up of 2 branches. Before it starts repeating itself, it would actually repeat itself decreasing this way, and it would increase that way. So the moment it starts increasing, it starts repeating itself over here. So the tan function takes 180 degrees to repeat itself. Now, if the period changes, and you're now wanting to draw from 0 to 90 degrees, then what you're going to have is, notice how I've sketched it. I went period with the zeros. Halfway, draw your asymptote. Halfway, draw your 1 and -1 values. Notice no amplitude, there's no maximum distance above the axis. So, this y equals tan 2x. Look, I'm not even going to write the values down. I'm going to go 0 degrees, and I'm going to write here 90 degrees. Then halfway, I'm going to have 45 degrees. That's my asymptote. And halfway, I'm going to have my 1. So at 22.5, I'm going to have my 1 value. And at 67.5, I'm going to have my -1. And then the curve behaves in exactly the same way, but it's just happening at different values because the period has been affected. Okay, so the tan function behaves in the same way with the period. It needs to have what I call them kind of not really quadrant angles, but in a sense almost quadrant angles, because the period is 180 degrees, so it's not going to go through all the 4 quadrants. Okay, so nice tan function. Halfway, fill in your asymptote. Halfway, fill in 1 and -1s, and then repeat. So if the question said go to 180 degrees, you would keep repeating that pattern. Or if it said go to -90, you would keep repeating that pattern. So at -22.5 degrees, you would have a -1, and you then have another asymptote. And so you keep on repeating the previous cycle, both left and right.
Okay, guys, I hope you're enjoying this revision session. If you need help, remember to post on the page or send an email to helpdesk@learnextra.co.za. Now it's time to take a quick break, but don't go away. We'll be right back. Welcome back, guys. We have some great news to pass on to you. We will be bringing you winter school from the 30th of June till the 20th of July, starting at 10 a.m. every weekday. To get the full schedule, visit our website, learn.mindset.co.za, and look for the winter school link. Join us, it's going to be a lot of fun. But now it's time to get back to the lesson.
If sine 16 is equal to k, so now we've got the ratio for sine 16, write each of the following in terms of k. So we don't want you to go and find out what k is and then try and write these in terms of that value. You actually need to write it in terms of the variable k. So if we have sine of 196 and we would like to write it in terms of k, we would like to rewrite the 196 in terms of the sine 16. Now, when you've got a little bit more of knowledge of how these things work, you can actually craft your own before you can actually go into these. But I'm actually going to answer them because they've already been written for us. So, grade 11's tips on how to handle this. 196 degrees, your first job is to always write a little Cartesian plane with 90 degrees, 180 degrees, 270 degrees. Fill in your quadrant angles. And then decide which quadrant is the terminal A for 196. Now, we all know that 196 is going to be here. So that's how big 196 is. Your question is to reduce that 196 to sine 16. Okay, so the first thing is position. So we've identified that the terminal ray is in quadrant 3. Now, if it's in quadrant 3, you now, on your Cartesian plane, you should have also been able to write down what happens in quadrant 2, what happens in quadrant 3, what happens in quadrant 4. Okay? So in quadrant 3, every angle can be rewritten as, let's just get this, there we go. Every angle can be rewritten as 180 degrees plus some acute portion that is going to give you the 96. And can you see that that acute portion is 16 degrees? Now, from that version, we are going to get that this is the same as, because we're in quadrant 3, and in quadrant 3, all students take coffee, there we go. The T means that only tan in that quadrant is positive, which means it's going to give us a negative ratio of sine 16. So first thing is to look at the position. Second thing is to be able to rewrite it in terms of the angles in the quadrant. And the fourth thing is to look at the sign. Is it going to be positive or negative? Because grade 11s, it's always a positive ratio or a negative ratio. It can't be anything else but positive or negative. So that's what we would do. And so now I've rewritten it in terms of sine 16, which means that my ratio is going to be negative k. Same ratio numerically, but it's actually going to be negative. Okay, so then cos of 74 degrees, if we do it over here, cos of 74 degrees, how do we treat acute angles? Because grade 11s, 74 degrees is an acute angle. So if it is acute, why are we going to reduce? We only reduce angles that are larger than 90. Well, acute angles can be written in terms of their cofunction. So cos of 74 degrees is the same as, let's drop it, we get sine. But the moment you drop the co, or you add the co, you have to write it as a complement. So it would become 90 minus 16. And the moment it becomes 90 minus 16, we then have sine 16. And notice that because 90 minus is not in any of the second, third, or fourth, they don't change sign. Because cos is 74, it will be positive. So your acute angle will also be positive. So this would be what we call our COCO rule. When we take the prefix CO, we drop it, we only get sine, but then you've got to rewrite that as a complement of 74. The complement of 74 is 90 minus 16. So we get sine of 16. Now, what about C? We have the sine of negative 344. Now, grade 11s, I'm going to show you two ways of how to deal with negative ratios, because one of the goals of our lesson today was to look at what happens with the reduction formulae for negative angles. And I'm going to look at it in terms of two ways. We could look at it as the sine of 344. So the sine of a negative angle is the same as the sine of the positive angle as long as you make it negative, okay? Or if we look at the Cartesian plane and we try and identify where is negative 344, negative angles in mathematics are measured in the opposite direction. So we would be going this way. This would be negative 90, this would be negative 180, and this would be negative 270. So can you see where negative 344 is going to lie? So we're going to rotate all the way to quadrant 1. So that's where the terminal ray is for negative 344, okay? Which means every single angle has got a coterminal angle. And if I rotate in an anti-clockwise direction, then how big is this white angle, the coterminal angle? Do you agree? It's 16 degrees. Okay, so my alternative is to rewrite it as the coterminal angle. And some people love to work with the coterminal angle and to say, well, this is exactly the same. So sine of negative 344 is exactly the same as the sine of 16. They are coterminal angles. And you would just write in a reason, coterminal angle. Okay? And in that way, you've rewritten it as sine 16 because you've worked with a coterminal angle. So one way is to go via the coterminal angle. The other way is to go through what I call the rules for negative angles. And here they are. Firstly, if you take sine of negative a, you will get it to be negative sine a. If you take cos of negative a, that's the same as cos a. In other words, when we plot the ratios for a and negative a, we get exactly the same ratio. And when you take tan of negative a is equal to negative tan a, you'll observe something very interesting, that the rule for cos is the only one that is positive. The other two are both negative. Can you think of a quadrant where that is also true? That behavior happens in quadrant 4. Okay, so it's similar to quadrant 4. Just make this a bit tidy, a little bit untidy. Okay, so behavior is the same. So your rules are according to quadrant 4 rules. So if we go back here, can you see? I've taken sine of negative 344. What happens in quadrant 4? Sine is negative. There we go, negative sine of the additive inverse. So you change the sine of the angle, you change the sine of the ratio. And now grade 11s, from there, you would just operate with the same rules. Same thing as we've done before, position. That would be quadrant 4. So that would be 360 minus 16. Okay, and now we look at the quadrant. Quadrant 4 means the sign changes sign, so that becomes negative sine 16. And if we just keep going, we get positive sine 16. Now, if you look at these two approaches, you will see that this one certainly goes through a lot more work. It goes through the rule for the negative angle. It goes through the reduction formulae into fourth quadrant, and then finally simplifying. The coterminal angle, look how quickly we got to it, because we had the position of negative 344, and then the coterminal angle was just at angle sine 16. So we actually got there much, much quicker. And grade 11's up to you. Whatever you feel more comfortable using, go for it. But I've given you two options to work with: reduction formulae of negative angles. All right, and then the last one, 1 minus cos squared 164. Let's make that orange. 1 minus cos squared of 164. I've specifically asked for a squared function because grade 11s, this is a very popular pothole in trig. For some other reason, let's rather look at it so I can explain to you what I'm talking about. If I look at numbers, pure numbers, I'm just staying away from the trig for a little while. If I ask you for 2 squared, what do you get? If I ask you for negative 2 squared, what do you get? And if I ask you for negative 2 squared, what do you get? Do we get the same value in all 3 cases, or do things differ slightly? Well, 2 2s are 4, so we have got no problem with that. Negative 2 times negative 2 is positive 4, so we've got no problem with that. But what about negative 2 squared? Grade 11s, let's not make the mistake of understanding that this negative here means that we want the additive inverse of 2 squared. So this is forcing us to have just positive base 2 squared, and so we actually get negative 4. It's the additive inverse. So this is the additive inverse of that value there. Okay, there's a very famous mathematical symbol. It's called the additive inverse, and we get, as the moment we attach that negative sign and we've made it the additive inverse, we've made that value the additive inverse as well. So this does not ever mean that you are making or that you are getting a positive number, like when you have your base round, where you have your base inside those brackets. Base inside the brackets makes it always positive, but that isn't. And that understanding is going to come into this trigonometry. Right, and where do I begin? With just cos 164. I just want us to look at what happens with cos 164. Grade 11s, reduce this. First question, position. Which quadrant is a terminal ray in? Quadrant 2. Good. So this is going to be the same as cos of 180 because I'm in quadrant 2, and it will be the supplement of which acute angle? Don't have a problem. 180 minus 16 gives me 164. Now, if I reduce this, because at this stage cos 164 is negative, at this stage it's negative, but the moment I make it cos 16, remember cos 16 is now positive because it's an acute angle. So second quadrant angle comes down as being a negative ratio. So that's negative cos 16. That is the linear. If I take the quadratic, I want you to watch carefully what happens. Cos squared 164 becomes cos squared 180 minus 16. But now here's the problem, grade 11s. Here's the problem. Is that most grade 11s will want to now write negative cos squared 16. And can you see what the problem is with the mathematics? Is that you're now making a squared function, which should always be positive, you're making it into a negative. And the only reason this happens, grade 11s, is because this squared is kind of next to the function. It's not really saying that this squared over here should actually be outside. So now we get negative cos 16 times negative cos 16 is simply cos squared 16. So when you've got a squared function, you can go straight there because every single square, whether it's positive base or negative base, will always become positive. So we don't actually have to go through that. But, big but, if you write over here that this is the same as negative cos squared 16, then we have a major problem, and you're going to get naught for your question because that's not the same thing. So you must really be aware that this exponent over here, which we usually write for simplification means, when we have a negative function, we should actually put a bracket and the square on the outside, just so that we don't get the notation incorrect. Because if notation is incorrect, I'm afraid the whole thing is incorrect. It's not mathematically logic, and therefore you will lose marks. So grade 11s, be very careful about that. So we looked at the linear, we looked at the quadratic, and now our real question was to find out what is 1 minus cos squared 164. And we said that it was 1 minus cos squared 16. But you'll notice at the beginning, we only had sine 16. So how on earth do we connect sine 16 and cos 16? What is that connection? That little application that we use to connect those things? Anyone know? Some of you may have done it in class, some of you may not, some of you may have heard it, but there is a connection between sine of an angle and cos of the same angle, and it's via the squares. So we will do a bit more of that next week, but cos squared 16 plus sine squared 16, and I'll give you a moment, punch that into your calculator. What do you get? And let's also do it together. So cos 16, and we're going to square it, plus sine 16, and we're going to square it. Oh, wow, isn't that magic? That's absolute magic. It's called a square identity, and we have that. Well, you should be asking me, does it work for all angles? Test it. Cos squared 17 plus sine squared 17. Test it on your calculator. What happens? So if I take 1 minus cos squared 16, can you see? It equals to sine squared 16. So we just want to remove this. I don't know where that comes from. So we've got, that's equal to sine squared 16. And remember, we were given sine 16, so we're given a, or it wasn't a, it was actually k. That's in fact equal to k squared. Right, so very popular question, being able to work with the acute angle into quadrant 2, quadrant 3, quadrant 4, negative angle, cofunction. Got to be able to do that with any angle that you're given.
I think it's time for a break now. Don't go away. We'll be right back. Welcome back from the break. Let's not waste any time and get straight back to today's revision lesson. Over to you.
Prove the identity that 1 over cos A minus cos A all squared is equal to tan squared A minus sine squared A. And the best way of handling any identity is always to work with the side that appears to have a lot more operations and a lot more work. If I look at both these sides, I think they've got equal amount of work. They've each got 2 terms. Maybe the left-hand side's got a square that I need to multiply out. So let's start with the left-hand side and see where we go. Okay, so my left-hand side, I have a bracket that I'm squaring. So just to facilitate my product, I'm going to write it out twice so that I don't forget. I find that my grade 11s forget a lot to get my OIs, my outers and my inners, the product of the outers and the inners. So you forget that middle term as we talk, okay, that should be a minus, not a plus. Let's just fix that here. So we've got, okay, so if we multiply that out, we've got inners and we've got outers. So we've got a 1 over a cos squared A, and we've got a minus a cos multiplied by its reciprocal. What is a number multiplied by its reciprocal? Always 1. So over here, I'm getting a negative 1, and over there, I'm getting another negative 1. So I'm getting a negative 2 as my outers and my inners, and then my outside ones is plus cos squared. So I've got a fraction, and that's why earlier I said we need to get in tune with algebraic properties, because to multiply that out, I now have a 1 minus a 2 cos squared A plus a cos to the 4A. So I've added up my fractions, and I really don't have much more room for maneuverability, because that is really a trinomial, if I wanted to factorize that, all over cos squared A. Another way of looking at this would be to say, let's firstly, before we multiply out, let's just collect our denominators or collect our fractions by adding the 2 terms. And we now have a 1 minus a cos A, or a cos squared A, which I've got as, okay, actually let's in the denominator. I don't have, let's just do that again. So we've got here, common denominator is cos A. This fraction's got a 1. That fraction needs a cos squared A. And then I need to square everything, which lands up to be, if I look at this version now, I'm getting a denominator that's got a cos squared A, and I've got a numerator that's got a 1 minus cos squared A. Now, from our notes, do you remember where are our notes? 1 minus cos squared A would be sine squared A, or 1 minus cos squared A is sine squared A. So have your notes next to you just to confirm. So 1 minus cos squared is sine squared A, and I am now squaring that. So it's actually sine to the 4. So I've actually been able to simplify it slightly better in that I've been able to get it into sine squared A instead of having all these in terms of cos. Okay, but let's look at the right-hand side. I've been able to work with the left in 2 different ways. Let's have a look at where do we go with our right-hand side. We've got a tan squared minus a sine squared. Tan squared A minus a sine squared A. Right, grade 11's decision time. What do we do with tan? Now, the whole thing about simplifying trig expressions is that we would like to get them either into sine or cos terms, because we can get most identities into that format. Why? Simply because if we're adding terms, then we could add the like terms, and if we're multiplying or dividing, we could then work with like factors, or we could divide like factors as well. So there is a purpose behind the identity simplification. We're trying to narrow things down to have it either in terms of sine or cos. Now, when we've got squares, we would work with a square identity to reduce that into one term. But if it was tan, then I could actually say that I have a quotient identity, a fundamental identity that changes my tan into sine over cos. Because I've got a tan squared, I'm going to get the numerator squared as well as the denominator squared. So that's cos squared A. And then I'm going to minus sine squared A. Right, then I've got 2 fractions, so that's over 1. So this is going to be cos squared A as a common denominator, and I'm going to get sine squared A minus sine squared A times cos squared A. So all I'm doing is I'm adding fractions. You've got to be very good with the algebra in order to be able to add fractions and to be able to factorize, etc. So the reason you've done grade 9 and grade 10 algebra is really as a support structure for the trigonometry, which uses a lot of those algebraic properties, adding fractions, being able to factorize, being able to multiply brackets, all that kind of thing. So let's see where we go with this fraction now. Can you see that I have 2 terms in my numerator? And do you notice something special about this term and something special about that term? It's actually equal to sine squared A minus, okay, let's just go back there. Right, it's actually got a common factor of sine squared A. So if I take out sine squared A, what am I left with? This term I'm left with a 1 minus a cos squared A. Okay, so I'm really doing algebraic work here, but utilizing, in place of our usual x's or y's or a's or b's, we're actually working with trig terms. That's really all that's happening. I've added 2 fractions together. I've got a common denominator. I've made those equivalent fractions. And from the equivalent fractions, there was a numerator that needed to be simplified, and it had a common factor, so I've taken out a common factor, and I'm left with a bracket all over my cos squared A. And now we see that in the numerator, I've got this 1 minus cos squared a, which grade 11s, if you've got your little notes next to you, you will see 1 minus cos squared a is the fundamental identity, but in a different version, in the sine version. So it's sine squared a multiplied by sine squared a divided by cos squared a. And that gives us our sine to the 4a over cos squared a, which is, if you remember, that blue version that we worked out. Here, it was a little bit complex in getting the trinomial out, because we would need to play a little bit with these and change them into sine, and that was quite tricky, I think. So it's easier to just take the bracket, first simplify the bracket, and then square it. There is always a decision-making in terms of whether we should expand or whether we should keep it in the bracket first. And I often tend to keep things together before expanding, because expansion oftentimes leads you to have to come back and factorize. So in this case, it was a good way, just keep it together. Okay, we had to solve cos theta equals negative 0,102. First thing you need to check, have I solved for the trig ratio? Is my trig ratio by itself? It's got no coefficients, it's got no terms. Good, we're good to go here. It's been isolated. The moment you've got that, you want to use your calculator. But grade 11s, I want you to be smart, and I want you to think about it. If your ratio is negative and you put it into the calculator, what kind of angle is the calculator going to give you? You mustn't just think, oh, this machine's going to enlighten my world and it's going to make things easier for me. The machine does not make something easier for you if you don't understand what the machine's giving you. So if my ratio goes in as negative into my calculator, what is the calculator processing to give me an angle back? What's it doing? And what will it give me? You must always predict that that calculator is going to give you an obtuse angle. Okay, so let's see if the calculator is going to do that. We take there, negative 0.102. What is it going to give us? We said an obtuse angle. Let's see. There we go. An angle larger than 90 degrees. And we have found that it is obtuse. So I'm happy with what it's giving me. Then let's look at the sine, because somebody asked about sine. How do we get, I think one of the mindsetters asked, how do we find the second angle of sine? And I think the best way to show that is with a picture. Pictures tell a story. Okay, so my sine curve, if my angle is positive, my calculator is going to give me this angle. So if my ratio was positive, it's going to give me that one. It's obvious that this angle over here, because it's symmetrical about the 90 degrees, this distance from 0 is going to be the same distance as that is from 180 degrees. So if I take 180 degrees minus that value, I'm going to get the second one. So to answer your question about how do I get the second angle of sine, it's always the second angle in quadrant 2 is 180 minus the calculator angle. And then you will ask, will it be the same if the ratio is negative? And the answer is yes, because we saw in the first segment that if my ratio is negative, sine is going to give me the fourth quadrant angle. And if you say 180 minus negative 30, you would be getting a third quadrant angle when it's negative. So same formula when the ratio is negative as when it's positive. And that's what I love about this formula, is it doesn't change for the different cases. The case changes, the formula stays the same. Really good. Right, so here, what's missing is that the ratio is not by itself. So sine A is equal to 0,785 divided by root 3. Leave your process steps in the calculation, because when you want to check your work, you want to be able to see what the processes were. Otherwise, it takes you a while to pick up where you may have gone wrong. So from here, we're ready to find the general solution. So we have A equals whatever the calculator gives us for that, 0,785. So we have second function sine, and we had a 0.75 that we were dividing by the root of 3. And let's get out of that and let's close that. So what does that give us? It gave us 26,95. Were we expecting that, an acute angle? Yes, because the calculator has been programmed to give us the acute angle if it's positive. Whether it's sine, cos, or tan, you're always going to get an acute angle. When it's sine is negative, it's going to give us the fourth quadrant angle. When cos is negative, it's going to give us the obtuse angle. And when tan is negative, it's going to give us also the fourth quadrant angle. So we need to know the cases for the obtuse, for the negative ratios, what is being programmed into the calculator. So it's 26,95, which really rounds it up to 27 degrees. So A is 27,0 degrees plus, it says correct 1 decimal place, so you must show the decimal place. And then the sine is periodic over 360, or A equals second angle of sine is always 180 minus the calculator angle plus k 360, where k is an element of the integers. And that gives us, on your calculators, you can just go minus 180, knowing that you want the positive value of that. So that's 153. 153,0 degrees. So we get an acute angle and an obtuse angle. So here's my obtuse one, where if you go periods of 360 degrees, you'll get it over there, and over here you'll get that angle there. So it goes off to infinity. So the whole thing about the general solution is that your graphs continue, they oscillate to infinity. So you, unless your domain tells you to restrict your solutions, you're going to have infinite amount of answers. Okay. I think that was the negative ratio. What happens with the negative ratio? So let's do sine A as a negative 0,785. Let's talk our way through this. If my sine ratio is negative, what angle has the calculator been programmed to give us? The calculator gives us this value here, gives us this quadrant 4 angle. So that is the first angle it gives us. The other angle that we'd like is the third quadrant angle there. And for that, I'm just going to use 180 minus this negative portion, which is the same. So that would be 180 minus the calculator angle. Just for this case, where this is the calculator angle, because it's negative. Okay, so general solution will be calculator angle, A equals, let's go and find it. Sine of negative 0.785, and I'm dividing it by root 3. And what are we expecting to get? It's the same ratio as before, but it's negative. So we're not going to get 27 degrees, we're now going to get, awesome, negative 27 degrees. So negative 26,95, which we've rounded it off to negative 27. So it's negative 27, 0. Why is it 360 degrees? Because the period of the function, or A equals 180 minus the calculator angle, and all that gives us 180 plus 27. So let's just take the negative of the answer, which is 27. So it's really 180 plus 27, which is 207. Or 207 plus k 360, where k is an element of the integers. Right, so second angle, very clear here. It's always 180 minus the calculator angle. If the calculator angle is positive, this will give us an obtuse angle. If the calculator angle is negative, like in this case, it will give us the quadrant 3 angle, which is exactly where we want to be positioned. And then the nice thing is, grade 11s, you can take 207, you can take negative 27, you can substitute back in there, and you can see whether you're actually getting 0,785. You're going to get very close, because remember there was a rounding off to the nearest decimal. So, yeah.
We've come to the end of today's show. Thanks for joining me and for chatting to me during the show. Remember to visit our website, learn.mindset.co.za, to get the notes and to watch the videos from the term. Goodbye.